swear I saw it. There it is. Okay. All right, so go ahead and turn that in. Just kind of get them all somewhere up here, somewhere. Yeah, just put them on the corner over there. So, I mean, how did it go? All right. I'm hearing that the derivative was kind of ugly. Setting it equal to 0 was kind of bad. Very bad. Was it a quadratic? Yeah. All right. Okay, so you know, I presented this problem in the middle of class last time, where the problem that we had done was we were given the point 3, 1. 1, 2, 3, 1. Hey, that's the point right there. And we were trying to find the point on this parabola that was closest to it. Remember that? Yeah. And then I just like randomly was like, you know, what if we had another curve up here? What if we had y equals x squared plus 6. I just made that up. And this one was y squared equals 4x plus 1. And I said, you know, could we find the points on these parabolas that are closest to one another? And then I said, no, we're not going to be able to do it, right? So it's going to take probably some calculus 3. So I went home and messed with it. And it does take some calculus 3, but I think it would be even a challenging problem for my Cal 3 students. Because it turns out that to do this, you're going to have to solve a system of nonlinear equations. So systems of equations is something you study in college algebra. But those are always linear equations. So this turns out to be a system of 6 equations, 6 unknowns. It's nonlinear, which makes it very difficult. In fact, I kind of surrendered to it because it was just so bad. So I had the computer solve it. So this is just so you can see this. I had my computer solving. I had basically the 2 points I'm looking for. One lives on one parabola, the other one lives on the other one. I call this one x1, y1, and this one x2, y2. And then there's other stuff you have to do, which I won't get into. But the computer, as you can see here, I put in here, solve this equation, that's one of the equations, and this equation, and this equation, and this equation, and this one, and this one. There's 6 of them, and solve them for x1, y1, x2, y2, and then don't worry about this. And it had trouble. So solve was unable to solve the system with inexact coefficients. The answer was obtained by solving a corresponding exact system and numericizing the result. Okay, so that means that it had trouble. All right, the computer had trouble. But it was able to get it. And it gave me this solution. This was the only solution it gave me for x1, y1, x2, and y2. And I went ahead and plotted those. And the black dots are the solutions that the computer gave me. And I'm pretty convinced that that's correct. Zoom this out here. So what I've done is this is calculating the distance between those 2 points. And if you move, I'm moving this red one around, and then I can move this green one around. And if you mess with it, you can kind of see there's no way to get any better, any smaller distance than about right here. Somewhere around 3.51 something is as good as you can get. If you try any other combination of points, it doesn't appear that you can get it any closer. Very difficult problem. I wanted you to see that. You know, I presented it as kind of like, I wonder, and then it wound up being challenging. But I wanted to give you tell you there was a solution for it.
What type of thing did you have to use?
Lagrange with 6 unknowns in 2 constraints. Yeah, so it was, so you had to set the gradient of the function of 6 variables equal to the gradient, lambda times the gradient of the first constraint, plus mu times the gradient of the second constraint. It was not pretty. All right, so yeah, and the part that's hard is when you have to solve, and that's the part that I had trouble with. So I guess my point to this is that even though I was able to employ a method to solve it, I definitely had to rely on a computer to do it. Like, I'm not quite sure I could have solved that system of equations. It was that tough. So it's a good thing we have. I did mess with it, but I just was messing with it at home, and I recognized how difficult it was going to be, so I had the computer do it. And when the computer had trouble, I said, well, then I'm definitely going to have trouble. So
the computer was like, no.
yeah. All right, that's it. I just wanted to share that with you. All right, today we are going to move into a new topic, and it is antiderivatives. So this is kind of the beginning of Cal 2. You will in Cal 2 spend a lot of time doing antiderivatives. And so I don't know, I thought about kind of doing a recap of what we've done in Cal 1 or just starting antiderivatives. You don't want to just start? Recap. Now, if we can recap at the end, we'll recap at the end. Let's talk about an antiderivative. All right, there's some definitions here. Okay, a function capital F, is called an antiderivative of little f on some interval I if the derivative of capital F is equal to little f for all x in the interval. All right. What? All right, if f, next thing, if f is an antiderivative of little f, then capital F plus c is the most general antiderivative of f. And here c is any constant. So what's going on here? Let's see. All right, so let's say that we have some function. Let's take some function f of x equals 2x. And what we've done in this class is I've given you functions and we've taken its derivative, right? It's always been, here's the function, take its derivative. The question now is this function the derivative of some other function? So did that come from taking the derivative of something? And I hope it's obvious what you would have to take the derivative to get that? X squared, right? So we would say capital F of x is equal to x squared is an antiderivative of that, right? I said is an antiderivative. I did not say is the antiderivative, because that's not the only answer. What would be another answer that would qualify as an antiderivative of this function? Yeah, so I could say x squared plus 5, right? Or minus 5, or plus 2, or minus 2, or any number out there, right? Because when I differentiate this, that's going to go to 2x and that's going to go to 0, right? Understand? So since there's an infinite number of antiderivatives. Do y'all see that? But they all have to look the same way. They all have to look like x squared plus some number. You can't have like x cubed out here or something, because then the derivative wouldn't be this, right? So these are all antiderivatives, but we say capital F of x equals x squared plus c is the general antiderivative. So this covers all constants that you could possibly put out there. This c right here is known as the constant of integration, but I haven't even defined integration, but I'm just going to go ahead and let you know that's what it's called right now, and we can talk about integration later. It is the constant of integration. So every single time you have a function and you find its antiderivative, you will always have to have plus c out there. Because no matter what your function is here, when you take its antiderivative, you could always have that constant out there that when you differentiate it goes away, right? Okay, so let's try another one. Oh, wait, I wanted to show you a picture. try and show you the relationship. Okay, so here's the exact example that I just gave you. All right, so we started out with little f, right? Little f was 2x. That's this red line. And the antiderivative that we found, the first one that we found was just x squared. And it was this parabola right here, right? That's x squared. But we said it could be any parabola x squared plus a constant. So any of these would be okay, right? Any of those. So what we have really is what we call a family of functions. All of these parabolas qualify as being antiderivatives of 2x. So what makes, do y'all understand? These are all just x squareds moved up and down. So what makes them all antiderivatives? Well, the idea is this. Can you all see those tangent lines? So if I go and I pick an x value, so I go and I pick an x value and I look at the slope of the tangent line on any one of those curves, right? Doesn't matter which one I pick. If I go to an x and I say, what's the slope of the tangent line? All of these functions within this family all have the same slope, right? And therefore, the derivative of the black function is always the same, no matter what. Yes? And that's why 2x, right, gives us that slope, is the same for all of them, no matter which x we pick, right? So that's why we get a family when we go backwards, right, from 2x back to its antiderivative. Okay. Let's do this one right here. 3x squared plus 10x plus 6. All right, so if we have that, what is the general antiderivative? So we have to be careful here, okay? This is where we really want to start being careful. Do you remember that when we took derivatives, that if we had separation, addition and subtraction between things, terms, right, we could differentiate them individually, right? Well, when we're trying to find the antiderivative, it kind of works, well, it does work the same way. If you have addition or subtraction between things, you can look at the antiderivative of each one, all right? So for this, let's just try and think through what it would take to go backwards here. And then I'm going to give you a formula, but let's just try and mentally do it. So what would the antiderivative of this be? X cubed, right? That's what you have to take the derivative of x cubed to get this. Now, the only way you really know that is if you're very comfortable with the idea of what the derivative of x cubed is, right? If you're real comfortable with the derivative of x cubed, then it's obvious to see that this is its derivative, right? If you're still struggling with derivatives, antiderivatives is going to really suck because you can't see it backwards if you never saw it forward, if that makes sense, right? Okay. How about this one right here? This one's a little tricky. 5x squared. Okay. So 5x squared, you can't have the 10 here because you know that 2 is going to come down, right? And that 2 is going to hit that 5, become the 10. And then how about a constant, just like this? What's the antiderivative? Plus 6x, right? And then plus c. So that's your general antiderivative. And we can look at it again, like we did before. The red function is the quadratic that you were given. The antiderivative turned out to be a cubic polynomial. And this blue one is one of them, right? Any of those blue ones moved up and down would satisfy being the antiderivative. And again, we have an entire family of functions. That's too many of them. Let me get some out of there. And again, if we move around, you can see all those tangent lines have something in common, and that's they are all parallel, so you get the same derivative no matter where you are on the graphs. All right. That's it. That's antiderivatives. Have a good day. You're ready for Cal 2. So let's try some more. How about this? All right, I would like for us to find the antiderivative of this. Nope, we'll do it together. So you can already see that we're going to have some problems keeping track of what's going on. So let me rewrite this. This is really x to the 1/2, right? Minus 3 times x to the 1/5. We agree with that? Yeah. And now, I mean, y'all didn't seem to have much of a problem here with this, right? Like you were like, oh, x cubed. And then here you were like, oh, 5x squared. That's pretty clever. Y'all all got that one. That's good. But what about this? So maybe what we need to do is pause and think about this and try and formulate a formula that would help us do this. So I think the formula, we can establish it if we just think through it. So let's go back. Okay, so we're going to pause this and we're going to come back to it. Let's think about something here. Let's recall that if you had x to a power in Cal 1, right? X to a power, and you took the derivative of it, what happened? Power came down, and then we subtracted 1 from the power. Like that was the power rule, wasn't it? We called it the power rule. It's one of the first ones we learned, and we really liked it because we got used to it, and it became pretty easy to use. Then came the product and the quotient and the chain and all that, but there was your product or power rule. So what if we're trying to go backwards, though? What if we're trying to go backwards? So think about if you were going from here to here, right? What really happens? The n has to disappear, right? Yes. And the power here has to go back up 1, doesn't it? Yes. Okay, so let's try this. Let's say that little f is x to some power, and we're trying to find capital F. Right? We're trying to come up with a formula here. We're trying to think through it. All right, can you tell me right now, I'm going to leave a little space here. Can you tell me right now what the power on capital F is going to have to be? N plus 1. Whatever this is plus 1, because the power is going to have to come up, right? Because when you differentiate it, why am I saying it like that? Differentiate. When you differentiate it, it's going to go down to n plus, from n plus 1 to n. Right, so you would subtract 1 from this to get you to here, right? But you also have to do what with this power when you take the derivative? It has to come down, right? And in what we want in the front here is a 1. We don't want anything sitting out there. So whatever this power is that comes out, we want to wipe it out right away. And to wipe it out, why don't we just multiply by 1 over n plus 1? So think about what would happen here. If I took the derivative of this, the first thing that would happen is the n plus 1 would come out front, wouldn't it? N plus 1 would come out here and then cancel with n plus 1. And that would just be a 1. And then I would take the power and reduce it, which would give me this. Do you all see that? No? Yeah? No? Yes? Let me give you more examples. All right. What about this? Let's do x squared. What's the antiderivative of this? I think everybody is probably comfortable with the idea that, you know what, I should have put plus c out here. Sorry, plus c, just to be technically correct. Is everyone comfortable with the idea that the antiderivative of x squared is going to have x cubed in it? Yes. Because the power is going to have to go back down. And then if I told you to take derivative of this right now, the 3 would come out, but there's no 3 here, right? So you have to get rid of the 3. So I put a 1/3 out here. Do y'all see that? So what this formula is saying is this. If you have x to the n, right, x to the n, then the antiderivative, what you're going to do is you're going to take x to the n plus 1. You're going to add 1 to the power, but then you're going to have to put a 1 over that n plus 1 out front to kill off the n plus 1 when it comes down. Let's do another one. If we have f of x is x to the 7th, then it's going to be 1/8 x to the 8th plus c. Right? So the power would come down, but then that 8 would pop out and get killed off by the 1/8. Make sense? So this appears to be a new rule for us. And this rule, we actually call it the power rule. But not for derivatives. It's the power rule for antiderivatives. Let me give you another example. If you try and follow this formula, you're going to run into a problem, aren't you? What's going to happen? You're going to have capital F of x equals, you're going to add 1 to the power, right? So when you add 1 to -1, you get 0. So you get x to the 0. But more importantly, out front, you get 1 over what?
0.
1 over 0. And that's undefined. So it looks like the formula broke down, didn't it? It broke down. It broke down when this power was -1, right? It broke down. So this formula has an asterisk next to it, or a star, whatever you want to, however you want to do it. This has a star. This works for n not equal to -1. This formula is good. As long as n isn't -1, you can use this. So what happens if n is -1? Like, what do I do? I don't panic. I just rewrite that as 1 over x. And then I just remember that that's the derivative of something. That's the derivative of what? Natural log. That's the derivative of natural log. You just have to remember that one, right? Remember the derivative of natural log of x is 1 over x? Yeah. So in this special case where that n is -1, the antiderivative is natural log x. Plus c. Right? So we have this brand new thing called a power rule. I think you understand it. I think you get this. That what we'll do is, if we have x to a power, we want its antiderivative. We will add 1 to the power, and then we will multiply by 1 over whatever that power is. And we'll add c. So long as the power isn't -1. If the power is -1, antiderivative is natural log, and we're done. Yes? Okay, so let's get back to this one up here. This marker's really good. So the first thing I did was I rewrote the problem so that it looked like powers of x. I mean, rational exponents. Powers of x, that's fine. Do y'all remember in college algebra when y'all were first learning rational exponents as opposed to radical notation? I hope that your college algebra teacher told you the reason why we want to be able to do this is because in calculus that's the way we prefer to work with things. We want to see powers as fractions as opposed to radicals because when it comes to calculus, we work with those powers, right? All our rules are based on these powers as opposed to radicals. So, yeah. All right, here we go. So how about this one right here? We're going to do these separately.
2/3 x to the 3/2.
I'm going to go a little slower. Let me go a little slower. So I'm going to, the way that I do it when I'm first kind of learning it, teaching it, is I just first write down the x, and I'll go ahead and put 1/2 plus 1 up here, okay? Because that's n plus 1, right? Mm-hmm. And then out front, I'm going to put 1 over 1/2 plus 1 again. All right? That's what it is, right? That's the formula. I'm going to add 1 to the power, then I'm going to multiply by 1 over that. Now here, I have minus 3 times this, right? And do you remember when we took derivatives, if we had a constant that was attached, it came for the ride? Same thing going backwards. That minus 3 is going to come for the ride. So I'm just going to put minus 3. And then times, and now I start doing my little power rule on this. So I leave a little space. If you want, you can put here now. It's up to you. Then x to the 1/5 plus 1. And then down here, 1/5 plus 1. Make sense? And we can throw the plus c on now if you want. All right, what's 1/2 plus 1? And don't tell me 1.5.
3 halves.
That's 3 halves, right? That's 3 halves. So this is 1 over 3 halves. X to the 3 halves again, right? Minus 3 times 1 over 1/5 plus 1 is 6/5. And then x to the 6/5. Then plus c. Anytime you have a fraction like this, 1 over a fraction, it reciprocates. So it just becomes 2/3. And this is going to become 5/6. So I'm going to have 2/3 x to the 3 halves minus 3 times 5/6 x to the 6/5 plus c. I can do a little bit of cleaning up still. This 3 and this 6 can reduce out, and that can become a 2 down there. So I think a good final answer for this one is 2/3 x to the 3 halves minus 5 halves x to the 6/5 plus c. Box it up. Now there's some really good news here when it comes to antiderivatives. Really good news. You can always know whether or not you're right. How? Just take the derivative, right? If you take the derivative of this, you better get back this, right? So should we check it real quick? If we take the derivative of this, we pop that 3 halves out, right? 3 halves is going to hit that, and it's going to go away. It's going to become a 1. Then I'm going to reduce the power by 1. So 3 halves take away 1 is 1/2. So I'm here. So that's good news. Now here, when this comes out, 6/5 multiplies times 5 over 2. The 5's cancel. You get 6 over 2. That's 3. So you get a minus 3. And then you remove, subtract 1 from that power, and you get 1/5. So you will get that. Derivative of a constant is 0. I'm not going to go through and show all the little technical things, but checking it is nice. All right. We good? Okay, now we're done. Have a good day. No, I'm kidding. I'm kidding. I'm kidding. Okay, let's take a look at this one. Man, this marker is too good. I don't like it. It's too hard to erase. All right, let me show you the incorrect answer. And you can tell me what this student did. Yeah. Right, so this student said, oh, look, I've got a bunch of things that I can find antiderivatives of. I can find the antiderivative of that, that's 1/3 x cubed. Find the antiderivative of that, maybe a little bit of mental exercise there, but that becomes negative 2x squared, right? Antiderivative of 1 should just be x, and the antiderivative of that is that, and that is completely wrong. And the reason it's wrong is because when you took derivatives of quotients, it wasn't that easy, right? And I bet you anything, if you take derivative of this, you're not going to get that, because you have to do the quotient rule on that, don't you? So how do we undo something like this? This becomes very problematic. Can you already see that this is going to become problematic? But because I presented the problem this way, it's a very specially selected problem. You can do something first before you do any calculus, and that's you can split it up into 3 different fractions. You could have done x squared over x squared minus 4x over x squared plus 1 over x squared. You were allowed to do that because you had a single term in the denominator and multiple terms in the numerator. That means this is legal, right? Now let's simplify that. That's just 1 minus 4 over x, right? And then this last one is plus 1 over x squared. That's the same expression, isn't it? Now look, you have 3 separate terms. 1, 2, 3, right? They're separated by addition and subtraction, so now you can do them individually. You couldn't do that up here because of that division down here, right? Now, I need all of these to look like powers of x, like x to a power, right? So how about 1 minus, I could write this as 4x to the negative 1, couldn't I? And then this one I could write as just x to the negative 2. Do you know the antiderivative of 1? It should just be x, right? Because the derivative of x is 1. This was the special case, wasn't it? Wasn't this the special case? If you had negative 1 up here, the formula didn't work. But that's okay, because the antiderivative of this is just going to be natural log. This one, the formula should work. So I'm going to work this one out. All right? So here we go. Here's our answer. That first part that I've done up there was just rewriting the problem, right? That was just rewriting the original problem. Now the antiderivative, capital F, should be, we said x, right? Now, minus 4, the 4 comes for the ride, right? Minus 4 comes for the ride. The antiderivative of x to the negative 1, or 1 over x, is actually natural log of x.
Then you can move it forward to the x to the 4.
You could move this 4 up here. I'm not going to, but yes, you could. That would be a legitimate move. Now, the next piece, plus. Now I'm going to run my power rule on this. So I'm going to do 1 over negative 2 plus 1 x to the negative 2 plus 1, right? That's what the rule says. Then plus c. So this is x minus 4 natural log x. And then what about this? This is negative 1, right? 1 over negative 1 is still negative 1. So we get negative 1 and then x to the negative 1 plus c. You could rewrite this as 1 over x, like minus 1 over x, and then box it up, and that'll be your answer. Or you can leave it with a negative exponent. It doesn't matter. It's the same thing. Are there any questions on that one? Sure? Sure? Yes? All right, so I think, what you really have to do with this is practice, just like with derivatives. You've got to continue to try and get your brain used to doing that arithmetic. Let's see here. Okay, how about this? I know you all know what the derivative of sine is, but what's the antiderivative of sine? So what do you take the derivative of to get sine? negative cosine of x plus c. So make sure you understand what's happening here. If you take the derivative of cosine by itself, you get negative sine. That's not what we want. So we put a negative in front, and that will account for it. And you get double negative, which will create your positive, right? Okay, what about cosine? What if we have little f of x is cosine x? The antiderivative of that is just sine x plus c. There we don't have to worry about a sign, right? The little negative doesn't pop out when we take the derivative of sine. We don't have a negative. It's just cosine, so that works. Yes? Okay, sine, cosine. What about tangent? Ooh. Uh-oh. The derivative of tangent is secant squared, right? But that's not what we're asking, right? We're saying, what do you take the derivative of to get tangent? How did you get these? How did you know it was negative cosine? How did you know it was sine? Because you know the derivative of sine is cosine, right? And you know that the derivative of cosine is negative sine. You slapped a negative out there. So the way you knew these is because you knew the derivatives of sine and cosine somehow give you sine and cosine. But with tangent, we never took the derivative of anything and just got tangent out. That never happened, right? Never did.
We could rewrite it as sine over cosine, right?
As what over what? You could rewrite this as sine over cosine. I agree with that. Yeah, so how do we get to that? You cannot just take the antiderivative of each one separately. You can't do that. That would be like trying to do on the previous problem, doing the same thing, doing it separate. No go. Cal 2 would be a lot easier if that's what the rule was. You just take derivative top or antiderivative top and bottom and be done. But that also would have made product rule and quotient rule non-existent, right? So yeah, this is tough.
Could you split them up to sine and then plus 1 over cosine?
You could do sine times, yeah, and that would cause a problem because you can't do them separately then. So I don't expect for you to know this. I mean, you wouldn't. That's the reason I put it up here is to show you, look, we're already jammed up, right? We already have something we can't do. Now, if you want to know what it is, here's what it is. It's natural log of secant x. That's the antiderivative. What? I'm going to show you how to get that next class, all right? But let's just see why it works.
Yeah, why not?
Yeah, we'll see. We'll see. But let's just check it. I said we could check our answers, couldn't we?
Yeah.
Okay, so let's take the derivative of this. Hold on a second. Wait a minute. Wait a minute. Okay, let's work through it. It's not sine? No, it's secant. Okay. It's not cosine? Negative. Yeah, this should work. Okay, let's do it. So what's derivative of natural log of something? 1 over it. So this is 1 over secant x times the derivative of secant x, which is just secant x tangent x. That's chain rule, right? Derivative of natural log of something is 1 over it times derivative of what's inside, derivative of secant x, tangent x. And the secants cancel. And you just get tangent. Right? Now, how would you ever have seen that? You wouldn't have. And we have to have a special way of doing something like this. And that's the first real technique that you'll learn to be able to do antiderivatives. It's called substitution. And that's the first rule, that's the first kind of technique. And there's a bunch of others, but that's the first one. All right? Okay, so just think about it. If I went to the next three trig functions, like secant, cosecant, and cotangent, all three of those, you're not going to know what they are, because we just don't have anything that you take the derivative of and get secant, or cosecant, or cotangent. So for the remaining three trig functions, I'm just going to say stay tuned, all right? How about this? How about e to the x?
E to the x.
Itself plus c. That one works real nice. The antiderivative of e to the x is itself plus c. So here's so far like a recap of what we've talked about. Antiderivatives. If you have x's to powers, you have a power rule. Unless the power is -1, and then it's the natural log. Otherwise, if you're trying to find an antiderivative, it's got to be something you know already. So you've got to know that the antiderivative of the sine is negative cosine. You have to know that the antiderivative of cosine is sine. Okay, so we'll rely on our knowledge from Cal 1 to be able to do common antiderivatives. That make sense? Now, recall from Cal 1 that if, I think they used S of t is a position function, then, oops, that says then the derivative of S of t equals V of t is the what? So if someone gives you the position of something as a function of time, so I tell you where something is at every point in time, its position, then the derivative, first derivative, would give you what? I heard it. Velocity. Do y'all remember us talking about this, or does this seem completely foreign? Well, that's why I'm asking you. I think we did, but I don't know how in depth we got.
You said the second derivative was acceleration.
And the second derivative is acceleration. And the second derivative equals the a of t is the acceleration function. I did talk about this, I think, because I showed you the formula d of t equals -16t squared plus v naught t plus d naught, and showed you how you can get gravity from this. No? Falling objects that fall on Earth? Okay, well, look, yeah, we didn't go in depth, okay, but I know that I have said something about this. So let me just recap, because it sounds like there might be some confusion here. Let's say that we have a function where we have time as our input, and this is going to be t, and then we have position, which is s of t, and that can be measured in feet, miles, whatever. And so what we basically know is everywhere that some object is at every point in time. We know where it is. Then if we take the derivative of that and graph it, so here's time, and now we graph its derivative. So the derivative is a different function, right? If we graph that derivative, whatever it is, this would give us our velocity at every point in time. So this function tells you where it is. This function is telling you how fast it's going at every point in time. And then the second derivative would be telling you, whatever that is the acceleration. Acceleration, velocity, position. Understand? You sure?
Yeah.
Okay. So to go this way, we're differentiating, right? What we're about to do is start here and go backwards. All right, so what we're going to do is we're going to start with an acceleration function. And I'm going to try and ask you the question of where is the object at every point in time? Listen to what I just said. I'm going to give you the acceleration of an object at every point in time. And from that, you are going to tell me where the object is at every point in time. I remember my dad and I driving down the road when I was in a calculus class, the first time I ever saw this. And to me, it was like, it seemed very profound. I don't know why. My dad didn't think it was a big deal. But I said, Dad, did you know that if you know the acceleration of an object at every point in time, that you can then tell where the object was at every point in time? And he didn't seem to buy it. He was like, I don't know about that, son. So we want to go this way, all right? What we're going to find is that we need more than just the acceleration function. We need a little bit more detail about what's happening in order to do this. But I just want to kind of give you a feel for where we're headed, all right? So I'm about to put an acceleration function up here, and I'm going to ask us to find the position function, all right? Yep, we're going to have something, some sort of conditions. All right, here we go. Was what? Yeah, it's just getting bigger, I think. This one right here? Oh, this one. That one, I don't know. I don't think that was there initially.
I think that is getting bigger.
This one is getting bigger, yes. All right, so here we go. Given a of t equals t squared plus 4t, find s of t. Now, I'm expecting that you understand when I put a of t up there, it's understood that that's the acceleration function. And when I put s of t, that you understand that's the position function. Yes? Okay, so a of t, remember, this is the second derivative of the position, right? So what we want is to go backwards once. Let's go backwards to the first derivative. From the second derivative, let's go back to the first. So wouldn't that be an antiderivative? Okay, so I'm going to write s prime of t, not double prime of t, should be the antiderivative of this. And our variable is t here instead of x. So I'm just going to do some power rule on that, right? So what's the antiderivative of t squared? 1/3 t cubed. And then antiderivative of 4t, 2t squared. And then plus c. Ah, this is the problem. See, I know that the antiderivative of this is a family of functions. I don't know which one. It could be any of these, right? That's a problem. So my dad was somewhat correct at this point because if we know the acceleration, we can come up with a family of velocity functions, but I can't tell you which one it is. All right? But let's proceed. Let's just keep going. Now let's go backwards from here to position. So we'll need to take the antiderivative again, won't we? So let's see if you can figure out how that's going to work. So we're going to do the 1/3 is going to come down for the ride, and then I'll have to do the antiderivative of t cubed, which is 1/4 t to the 4th. And that's where you can get the 1/12 from. And then here I'm going to have the 2, Then I'm going to have 1/3 t cubed. That's the antiderivative of this. And then plus some constant, but I need its antiderivative. What's the antiderivative of a constant? Constant times t. C times t. Right? Like if this was a 5, then this would be 5t, right? If this was -2, this would be -2t. Yes? But then plus another constant. But I won't use c. I'm going to use another letter d because they're not the same letters necessarily. They're not the same numbers necessarily. So this is a d, all right? So I have a family of functions now, right? The velocity function, this was v of t. And of course, this is s of t. But the problem is, I don't know exactly which function it is, right? There's an infinite number of functions in this family. So if somebody gives you acceleration, you can kind of get back to position, right? You need more information, though. So how much more information do we actually need to nail this function down precisely? It turns out that I only need 2 pieces of information. That's it. I just need to know, you just tell me the speed of the object at one point in time, or the position of the object at the speed of the object at one point in time and where it was at one point in time, or where it was at 2 points in time, or its speed at 2 points in time. So I basically need 2 pieces of information, and we call those initial conditions. So what I'd like to do is I'd like to run through this problem again, all right? So I'll say it's a new problem. If a of t equals t squared plus 4t, and v of 0 is 5, and s of 0 is 3, find s of t. So you see the difference in that problem? I've said, hey, here's the acceleration function. And along with that, the velocity of this particle or whatever it is, the velocity at time 0 is 5. And the position at time 0 is 3. So I've given you 2 pieces of information, haven't I? Its speed at one point and its position at one point. From that, we should be able to do this now. Okay, so let's see how we would do it. First, we take the antiderivative, right? So we would get to this point right here. Remember that point we were at right there? And we didn't know what c was? Well, now we can get c. Because I know that my velocity at 0 is 5. And this is your velocity, isn't it? So when I plug in 0 for t into this, it should spit out 5. So I'm going to use this. I want to keep these on the board. So this right here tells me that when I plug in 0 for t, I should get 5, right? That's what that says? So I picked 0 on purpose because I knew it would kill off a bunch of stuff and make this easy. Plugging 0 into the velocity function, which is the antiderivative of the second derivative, I get what? C is 5. C is 5. So this tells me C is 5. So now I can go to the position function right here, and I could replace this with 5. Now, this is my position function, but I don't know what d is. But again, I'm given some more information. My position at 0 is 3. So what would happen if I take this, plug in 0 into that? What would you get? So I'll do 112, 0 to the 4th, just so you know what I'm doing here. This is 2/3, 0 cubed, plus 5 times 0 plus d equals 3. So d is 3. So the final answer would look like this. The final answer would be S of t, my position function, is 1/12 t to the fourth plus 2/3 t to the third plus 5t plus d, but d was 3. So that is the exact position. That gives me the exact position of that object at every point in time. I still think it's pretty remarkable that if you know the acceleration at every point in time, that you can, and then just one piece of information about each of these, that you can tell me exactly where it is at every point in time. Y'all get this or no? Okay. So another way to look at it is when you take the antiderivative of this, you get a family of functions, right? You throw that into there, and that nails which one it is. That actually gives you the exact one out of that family. Then you take the antiderivative of that, that gives you another family of functions. But you use this information, it nails down exactly which one it is. Okay, let's do another one. I want to start this one from scratch. Are y'all getting sad yet? We only have like 2 more classes after this. Y'all starting to get a little depressed? Yeah. Okay, if a of t equals t squared minus t plus 3, and s of 1 is 4, and s of 4 is 3, and find s of 10. All right, let's wrap our heads around this again. I've given you an acceleration function, right? Then I've given you what? What is this? This gives you the position of the object at some point in time, right? Position. And then I've given you another position, right? 2 positions of the function at 2 different points in time. And what am I asking you for? The position of the function at some other point in time, right? So let's see how we can do this. First step, let's take the antiderivative, right? So the antiderivative of this will give me the velocity function. And that velocity function will be 1/3 t cubed minus 1/2 t squared plus 3t plus some constant, right? Agree? All right. Now, I'm not going to be able to nail c down because I'm not given any information about the velocity, am I? Which means I'm going to have to just go again to get back to position. I need to take the antiderivative again. So my position will be, so this is going to be the kind of the same thing we just did a second ago. Isn't that going to be 1/12 t to the fourth? And then this one minus, so you have a 1/2 out there, right? But what's going to pop out in front of that 1/2? A 1/3? So it's going to be 1/6. I'm not showing this work, okay? I'm just hoping that you could do this on your own paper. This is going to be 1/6 t to what power?